Hello guys, welcome back to my channel. And as I promised in my last video, I'm going to restart my high school calculus playlist. So if you have referred to, if you have been watching those videos that I made before there was a big gap, then you might realize that I stopped at differentiability. I ended after explaining the possible conditions for when a function is differentiable and when it is not. I gave some examples in the video differentiability 2, and after that I started doing this trig integrals playlist. So now, as I promised, I'm back with my uh, high school calculus playlist. So in this video we'll be doing derivatives, and we know conditions for differentiability. Now in this video we're going to actually acquaint ourselves with the rules of differentiation, or the rules of finding derivatives of functions. So before watching this video, I would strongly advise you guys to know your derivatives really well, or have like a sheet of derivatives uh, beside you for your reference during this video. So like always, let's get to it. So in this section we're going to be discussing the rules of the game, or what are the different rules of finding derivatives of functions that we should know before doing before actually finding derivatives. So the first rule is, say if you have the derivative, and we are going to only differentiate with respect to x most of the time. We haven't reached to the part of implicit differentiation yet. So everything is differentiated with respect to x. So the derivative with respect to x of a constant, so a here is a constant, the derivative of a constant is always 0. And this makes sense, right? Because calculus is the study of change. So stuff that doesn't change, basically stuff that is constant, is gonna result, it's quite uninteresting. So it's gonna yield 0. That's the way I look at this property. Now the next property is similar to this. Say we have the derivative, but instead of just a constant we have a constant times a function f of x. Well, as I said, calculus is a study of change. Stuff that is constant is very uninteresting, so you can just write it, just take it out of the derivative operator and then differentiate the function f of x. And I'm going to call this d over dx of f of x as f prime of x, just for a way more convenient system of writing stuff. So this property says that if you have a constant times a function, you can just take the constant outside untouched and then differentiate the function. Now say you have the derivative of one function plus another function, so it's a sum of functions. And don't worry, I'm going to do examples of all of these things collectively, because say if I did examples of this property number 1 after explaining property number 1, then if I did examples of property number 2, after explaining property number 2, then it would be kind of obvious to you guys which property to use. So after explaining all the properties, I'm going to do examples of them um, later on, so that you can dynamically see which properties to refer back to. Okay, so property number 3 is, say you have the sum of functions f of x plus g of x and you differentiate that. That is the same thing as the derivative of f of x plus the derivative of g of x. So you sort of split the derivative, and then, as I said, I'm going to be using this shorthand notation. So derivative of f of x is f prime of x, and this is g prime of x. Now the fourth property is similar to the third property, except instead of a sum, we have f of x minus g of x. So basically, this, like our third property, we can split as the derivative of f of x minus the derivative of g of x, and then again using this shorthand notation, we have f prime of x minus g prime of x. Now property number 5 is what we call the product rule. Well, we talked about addition, we talked about subtraction. What about multiplication of two functions, the product of two functions? Say you have the derivative of f of x multiplied with a second function g of x. Well, this becomes g of x multiplied with f prime of x, I'm directly using shorthand notation, plus f of x multiplied by g prime of x. So the way I look at this product rule is, say you have two functions f of x times g of x. You take one function at a time, and when you are, say, only considering one function, here we first considered f of x, the other function is sort of treated as a constant, plus then you consider the function that you ignored in the first part times the function that you considered earlier gets treated as a constant. So it's sort of one at a time kind of process here. It's sort of a queue. So f gets differentiated while g is waiting, plus then g gets differentiated while f is waiting. So that's an interesting analogy that you can probably use. So naturally, if we have a product rule, we should also have a quotient rule, right? So that's property number 6, our quotient rule. Say you have the derivative of the quotient of two functions, so f of x divided by g of x. So now our property says you treat g of the denominator function as a constant multiplied with the derivative of the numerator function, so g of x times f prime of x, minus, now you do the opposite, you take f as a constant and then g prime of x, so you divide the denominator function divided by the denominator function, but the whole thing squared. So now interesting way of thinking about this thing is, well, since f is in the numerator, so f is on top, so it sort of dominates. So that's why f is taken in for differentiation first. So it's taken in for differentiation first while g is waiting, minus this time, not a plus, because the way I like to think it, quotient, basically dividing, can be seen as glorified negation, right? And multiplication can be seen as glorified addition. So that's why we had a plus here, and that's why we have a negative. But just remember the order here. So as I said, f dominates, so you take f first while g waits, minus, because division is glorified negation, minus, now you do the opposite, f is waiting while g is taken in for differentiation, and divide by uh, the denominator function squared, or g of x squared. So that's probably an interesting way of remembering the quotient rule. So property number 7 is extremely important. It's what's called the chain rule, and it's considered to be one of the hardest properties to visualize uh, in the first sitting. But don't worry, I'll give you a good intuition, just like I did for the product rule and the quotient rule. So what if you have the derivative of f of g of x? So it's basically a composition of functions. So g of x is inside the argument of f. Is basically g of x is basically being taken as an input inside the function f. So the way I like to think about a composition of functions is, well, the outside function. So f is can be thought of as an outer wall, and this g of x can be thought of as an inner wall. So when you differentiate f of g of x, you can think differentiation is sort of shooting with a laser. So differentiation can be thought of as shooting with a laser. So what happens when you shoot a laser at a two wall system? So what's going to happen is the first wall is going to break, but you're still going to have the second wall intact, right? So that's the analogy that we use here, because the property says you differentiate the external function f prime, but you keep the second function intact inside as the argument of that differentiated f, times, well, okay, you've broken the first wall, and you still have the inner wall, right? And you think of differentiation as sort of a constant laser, so it doesn't stop only after breaking the second wall, breaking the outer wall. It goes on continuously even after the outer wall is broken, so it also breaks the inner wall. So eventually you're gonna also break the inner wall, so you're gonna have to multiply by the derivative of the inside function, or g prime of x. So outside wall broken is f differentiated with respect to x, but when you break the outer wall, the inner wall is still intact, right? So that's why g of x still intact inside f prime, although f got differentiated, although f got broken, the wall f got broken, but multiply, because you still have to break the inner wall, right? So multiplied by the derivative of the inside function. Inside function is sort of an analogy to the inside wall here. So you still have to break the inside wall. Breaking inside wall is basically differentiating the inside function with respect to x. And why this is called the chain rule is because, say if you had three functions, so f of g of h of x, so that will be like having three walls, right? And differentiating three walls is basically differentiating three functions is basically shooting a laser, continuous laser, at these three walls. So first time the first wall breaks down, so you have breaking down is basically differentiation f prime. But if when the outer wall is broken, the other two walls are still intact, right? So g of h of x is still intact here, times, well, now you go on to break the second wall. So what happens when you break the second wall? You basically differentiate the second function. But when you break the second wall, the third wall is intact, right? Because it's sort of enclosed by it's being protected by the second wall. So you have g prime of h of x. Okay, the now the second wall is broken, but the derivative is relentless, right? It goes on to break even the third wall. So now you also have to break the third wall or differentiate the third function in this case. So if you have, say, n number of functions, you'll have to, you'll have n walls, and you'll keep on repeating this process until you reach the innermost function or the innermost wall. And I'll give you an example of this which will drive the point home. So don't worry about that. Okay, so time to do some examples now. Example 1, we have to differentiate 5. Well, as property 1 suggested, the derivative of a constant is 0 and 5 is a constant, right? There is no associated x with it. This is just 0. Well, example number 2 now. We have to differentiate e times x squared. Well, according to our property number 2, we have a constant times a function. So you can just take the constant outside the differentiation, because calculus is the study of change, as I said, and constants are uninteresting. Stuff that doesn't change is uninteresting. So it's sort of like it's not the focus of our study, because calculus is the study of change, right? Stuff that doesn't change is sort of not our focus of studies. So that's why we can just take e, which is a constant, outside the differentiation. So the derivative of x squared, I hope you know your derivatives well, is 2x. So we have 2 times e times x. Okay, let's go ahead now. We have now the derivative of x cubed plus x squared. And as I said, by property number 3, you can, if you have a sum of functions, you can split it into a sum of two different derivatives. So here we'll have the derivative of x cubed plus the derivative of x squared. X cubed is, well, using the power rule, you just bring that exponent down, and then x raised to original exponent minus 1. So 3 minus 1 is 2. So that's why this is 2x. Great. So the initial ones are easy. So now we have to differentiate. Let's not take any polynomial functions. Let's deal with sines and logs. So you have the derivative of sine of x minus the natural log of x. So property number 4 says the difference of two functions can be expressed as the difference of two derivatives. So d over dx of sine of x minus the derivative of the natural log of x. So if you remember, the derivative of the sine of x was nothing but the cosine of x, and the derivative of the natural log of x is 1 over x. Well, that was our all our properties until property number 4. Now let's practice some product rule. So first example here. So they're telling us to differentiate x times the natural log of x. So it's a product of two functions. So as I said, product rule is sort of like a queue. So you can only take one person at a time, and one person at a time for differentiation. Meanwhile, the other function is just waiting for its turn. So we can say x, that's waiting, times d over dx, the derivative of the natural log of x. So it's the turn of it's the turn of the natural log of x to be differentiated while x is waiting, plus now the natural log of x is waiting because x is being differentiated, and there is a plus because product or multiplication is basically glorified addition, right? Basically adding many times a number with itself is basically what we define as a product, right? So that's why there's this addition and then one function at a time. So the derivative of the natural log of x is 1 over x plus natural log of x times what's the derivative of x? 1 times 1. So x will cancel out. You end up with 1 plus the natural log of x. So example number 2, we have to find the derivative of x cubed times the cosecant of x. So like we did for example one function at a time, while the other function just waits. So let's make x cube wait while we take in cosecant of x for differentiation. So cosecant of x is being differentiated, plus now let's make the cosecant of x wait. Cosecant of x while we take x cube in for differentiation. So if you remember the derivative of the cosecant of x, it's negative cosecant of x times the cotangent of x. So we have negative x cubed times cosecant of x times cotangent of x plus what's the derivative of x cubed? 3x squared, right? So bringing the 3 outside, writing the 3 up front, 3 times cosecant of x as it is because it was waiting in this part of the expression, times 3x squared, right? So we just multiplied with x squared here. So hopefully you could see easily how we can apply the product rule. It's time to move on to quotient rule, which is slightly more work than the product rule. So now we have to differentiate 2 over x divided by the tan of x. So as I said, the function that's on top sort of dominates. So you take that in first for differentiation while the denominator function waits. So differentiate the dominating numerator function minus, now flip it. So now the dominating function is waiting outside, times the derivative of the tangent of x. Now why I'm saying that you take the dominating function first, why I'm specifying this is because you have a negative sign, so order is important here. So order is important for the quotient rule, but we have to divide everything by the denominator function squared. So tan x, the whole thing squared. So now what's the derivative of 2 raised to x? What's the derivative of an exponential function? It's that same exponential function times the natural log of the base. Here it's 2, so natural log of 2. So this becomes 2 raised to x times the tangent of x times the natural log of 2 minus, well, 2 raised to x is weighting, so 2 raised to x times what's the derivative of the tan of x? Secant squared of x, right? Divided by tan of x squared is tan of x, the whole thing squared is tan squared of x. So that was our example number 1 under quotient rule. So let's do another example just to clarify things a little more. Now we have to differentiate this expression x plus sine of x divided by x plus cosine of x. So you take this entire denominator to be one function and the entire numerator to be another function. So as I said, the numerator is going to dominate, so you take that in first for differentiation while the denominator function is going to wait outside. So taking the numerator function first for differentiation, x plus sine of x being differentiated times x plus cosine of x minus, because why did I say minus? Because division is glorified negation, right? If you just keep on subtracting repeatedly, that's just dividing. So that's why minus here against a plus that we had for the product rule. Minus, now you take the denominator function in for differentiation. So the numerator function will wait outside times the derivative of x plus cosine of x. But that's not all. Why is the quotient rule a little tedious, a little more tedious than the product rule? That's because you also have to square the denominator function. So x plus cosine of x, the whole thing squared. Now time to differentiate all the parts that we indicated to differentiate. So x plus cosine of x, and to differentiate x plus sine of x, well, it's the sum of two functions, right? So property number 3, this is what's important, using properties dynamically, not just classifying stuff in terms of black and white, but using the properties as you go forward to differentiating a complicated function. And trust me, we're going to have real complicated functions by the end of the video. So property number 1, so the derivative of a sum of two functions is the sum of derivatives. So the derivative of x plus the derivative of sine of x. I'm just writing everything so that it's perfectly clear to you. And we have x plus sine of x as it is, and again you have to use property number 3. So derivative of the x plus the derivative of this lone cosine of x. But that's not all. You have to also divide this monster large expression by x plus cosine of x, the whole thing squared. So now we have x plus cosine of x was anyways outside. The derivative of x is 1. Sine of x differentiated with respect to x gives us cosine of x. And we have a negative sign. And we have x plus sine of x as it is. Derivative of x is 1. Derivative of cosine of x is negative sine of x. But don't forget, and I'm repeating, don't forget to divide by the function in the denominator squared. Many people forget to square the function that's below, that's in the denominator, and then their derivative calculation turns out to be incorrect. So always remember to square the function in the denominator. Now if you want, you can probably expand the bracket. X plus x times the cosine of x plus cosine of x plus cosine squared of x minus x plus x times the sine of x plus the sine of x plus the sine squared of x. I'm sorry, there was a minus sine x, and you still have to divide that by x plus cosine of x the whole thing squared. So well, the x's are cancelling out, and this cosine squared plus the sine squared will make a 1. So we'll have 1 plus x times the cosine of x plus x times the sine of x plus cosine of x minus sine of x divided by x plus cosine of x the whole thing squared. So derivatives can tend to be bulky and messy and tedious because we have quotient rule, and you'll see in a while that chain rules can make them even bulkier and crazier. Time to practice some chain rule, which is probably the most important rule of derivatives. So the first example that I think is worth considering for the chain rule is, say we have to differentiate the tan inverse of x but the whole thing squared. I'm going to use square brackets to indicate the influence of the derivative operator. So what's the external function? What's the outer wall? Let's work with the wall analogy that we had. So what's the outer wall? Well, it's the function. Let's call it f of x squared, right? Because tan inverse of x is being squared first. Then you have a tan inverse inside that square. And what's the inner wall? It's just the simple tan inverse of x, right? You can call this g of x. So as I said, differentiation is like shooting a laser. So you break the first wall while keeping the inner wall intact. So breaking is differentiating the external function. So what's differentiating f of x, or what's differentiating x squared gonna give us? 2x, right? But the catch is, instead of this x, we still have our inner wall intact, right? And what's our inner wall? Tan inverse of x. So instead of x, we write a tan inverse of x multiplied by, because now we still have to break the inner wall, right? Because the derivative is a continuous laser. It's relentless. It's going to break all the walls eventually. So, it's going to break the inner wall, and so breaking a wall is basically differentiating that function. And what's the inner function? Tan inverse of x, right? Because that was inside the second power. So derivative of tan inverse of x. So we have 2 times tan inverse of x as it is times, what's the derivative of tan inverse of x? It's 1 over 1 plus x squared, right? So this is going to end up with 2 times tan inverse of x divided by 1 plus x squared. So again, to clarify things a bit, let's do another example. Say now you have to differentiate e to the sine of x. So instead of drawing the inner wall and the outer wall every time, let's try to picture the inner wall and the outer wall. What's the outer wall now? It's just this e raised to x, right? But instead of this x, we have a sine x. because it's a composition of functions. It's f of x inside g of x, where f of x is e raised to x and g of x is sine of x. So you differentiate the external function, keeping the inner, you basically break the outer wall, keeping the inner wall intact. So you differentiate the external function. So derivative of e raised to x is just e raised to x, but since we're keeping the inner function intact, we just, instead of x, we write the inner function, the sine of x, times, now you break the inner wall. What's the inner wall? The sine of x. So you differentiate the sine of x. Since the outer wall is broken, you don't need to consider that for differentiation again. So this is going to end up with e raised to sine of x times, what's the derivative of the sine of x? That's right, cosine of x. Now let's just do another quick example over here. So we have the derivative of, say, the tan of the natural log of x. So as I said, you break the outer wall, keeping the inner wall intact. So what's the derivative of a tan? Secant squared of the inside argument, right? But since you're keeping the inside wall intact, we're going to write natural log of x as it is. So you differentiated the external function, basically. You differentiated tan to get secant squared. But instead of having an x that you would normally have for tan of x, we choose to keep the inner function as it is, because we only breaking the outer wall. The derivative laser is first breaking the outer wall, so you differentiated the outer function, but the inner wall is remaining intact because it's sort of protected by the outer wall. So natural log of x as it is times, since the external wall is broken, the relentless, merciless derivative will now break the inside wall, or now we get to differentiate our inside function, which is the natural log of x. So to simplify, we have secant squared of the natural log of x, and what's the derivative of the natural log of x? 1 over x, right? So this divided by x. So now for examples 4 and 5, I'm doing more examples, by the way, for the chain rule, because it's probably one of the most important rules of differentiation, and most mistakes occur when people mess their chain rule. Well, it's mistakes occur when people generally mess up their quotient rule or their chain rule. So we need, it's a healthy habit to keep on practicing the chain rule as many times as possible. So let's level up things a bit. Let's do harder examples now. Here we had two functions inside, one function inside the other, two walls basically in our analogy. Let's have three walls now. So example number 4 under the chain rule. So we have, let's define the function y to be the secant of the tangent of square root of x. So as you might notice, we have three functions and two are inside the first function. So it's like having three walls. Remember having the three walls that I described while I was explaining the chain rule to you guys. It's three walls and the derivative is a laser, so we have to differentiate both sides. So differentiating both sides with respect to x, we obtain dy over dx to be nothing but the derivative of this entire quantity, secant of the tangent of square root of x. So using our three wall analogy that we had for the chain rule, so we first break the external wall, so differentiate the most external function while keeping the inside part intact. So what's the derivative of a secant? secant of the inside quantity. Here we choosing to keep this intact. So the tangent of square root of x, secant, so derivative of the secant of a quantity is the secant of that quantity times the tangent of that quantity. So the tangent of the square root of x. Okay, so we've broken our secant x. So we took care of our secant of x. Now it's time to take care of the tangent of x, tangent function. So times, well, now we're breaking the tangent, right? So the derivative of a tangent is secant squared, but we're keeping the inside, the third wall intact. It's not yet broken. Square root of x. So we even got rid of our tangent now. So now the innermost wall, the innermost function, the square root of x, and we still have to differentiate the square root of x. So we have the secant of the tangent of square root of x times the secant of the tangent of square root of x times the secant squared of the square root of x times the derivative of the square root of x is nothing but 1 divided by 2 times the square root of x, everything in the denominator. And just to keep things in perspective, this quantity over here is our third or outermost wall. You know, this we obtained from the outermost wall, you know, according to our analogy. This secant squared term is because of our next wall, or like the middle wall. We obtained secant squared of square root of x by taking care of the middle wall, and then finally we obtained this 1 over 2 times the square root of x by breaking the innermost wall. So you know, that's just to bring into perspective that I'll probably just repeat myself. So we had secant of the tangent of the square root of x. So 3 functions and one inside the other kind of situation here. So 3 walls according to our analogy. So we differentiate the first function, keeping the inside part intact. So the derivative of the secant was a secant of an argument times the tangent of the argument. The argument, since we are keeping the inside function intact, is going to be the inside functions untouched. So secant of tan of square root of x times the tan of the tan of square root of x times, using the chain rule now we got rid of our secant, we move into our inside function, that the tan of, so then we look to differentiate the tan of the square root of x. So that's basically differentiating the external function, keeping the inside function as it is. So derivative of a tan is a secant squared of the inside function intact. Fine, we got rid of our tan then, but we still have our innermost function, our innermost wall that the derivative needs to break. So the derivative of square root of x, because that was the innermost function. So it's sort of like a derivative, you know, it's like going deep within function within a function within a function. It kind of might seem hard to visualize and difficult to cope with the chain rule of differentiation, but I assure you, if you practice a lot, you know, you'll all be sorted out. Example number 5 is way complicated. compared to what we did under chain rule. So let's call y as cosine of x cubed times sine squared of x to the fifth. So it's basically the product of two functions. So it's initially telling us to use the product rule, which this function times this function. So it's basically first telling us to use the product rule when we get down to differentiate. But even after uh, using the product rule, when we go on to differentiate cosine of x cubed, we have to use the chain rule because two functions, right? Cosine of x is one function, but then you have x cubed inside the argument of the cosine. But here the situation is way more complicated because you have three functions. You have first the sine that's first being raised to the second power, then you have a sine, and then you have x to the fifth inside the argument of the sine. So as I said, let's look at each of the functions stepwise and use the rules dynamically. Let's use the rules of differentiation dynamically as and when they're needed, as and when they appear. So differentiating with respect to x on both sides, we obtain dy over dx is nothing but the derivative of the cosine of x cubed times the sine squared of x to the fifth power. So let's use product rule. Well, let's make cosine weight now. Cosine of x cube is weighting while you differentiate the sine of x to the fifth, but the whole thing to the second power. That's exactly what the sine squared is. Plus now you do the opposite. Now you make the sine squared of x to the fifth weight while you differentiate cosine of x cubed. Nice. So we successfully identified that we have to use the product rule first. So now let's get down to differentiation business. So we have cosine of x cubed. So time to use the chain rule now because it's three functions. It's x squared, there's a sine of x, and there's x to the fifth. So differentiating the outermost function, keeping the inner stuff intact. So we have x squared. If you differentiate the function x squared, you have 2 times x, but instead of x we have the inner stuff that we promised to keep intact. So we have 2 times the inner stuff, sine of x to the fifth times the derivative of sine of x to the fifth power. Okay, we'll do this in the next step while we look at the other side of the expression. So we have sine squared of x to the fifth multiplied with, well, again we have to use the chain rule. So differentiating the external function is negative sine but keeping the inside x cube intact, x cubed times the derivative of x cubed, because now we want to break the inside wall, the inside function we want to differentiate. So you can write the 2 up front. 2 times cosine of x cubed times sine of x to the fifth. Now you want to differentiate the sine of x to the fifth. You differentiate the external function, which is sine, keeping x to the fifth intact. So you get cosine of x to the fifth times the derivative of inside function, now x to the fifth. So we're done with the first part of the expression. Let's look at the second part. Instead of a plus, why don't we put the negative up front? So we have a negative sine squared of x to the fifth power times sine of x cubed times what's the derivative of x cubed? It's 3x squared, right? And no more functions that are placed inside the x cube, so we can end with our chain rule here. So what's the derivative of x to the fifth? It's 5 times x to the fourth, right? Using the power rule. So 5 and a 2 will make a 10 up front, and we can write the x to the fourth up front to x to the fourth times the cosine of x cubed times the sine of x to the fifth power times the cosine of x to the fifth power minus, let's write the 3 up front, 3x squared up front, 3x squared times the sine squared of x to the fifth power times the sine of x to the third power. So we can, although each expression that you want to differentiate may seem complicated, but we can always split them into simpler elements that we know what rule to apply on, and then as and when each of the properties or the rules of differentiation are required, we use them. So for example, in the start we saw outright that this was a product of two functions, so we use the product rule first. Then when we applied the product rule, we saw that we had to differentiate sine squared of x to the fifth, and we instantly recognized that it wasn't any ordinary function but a composition of three functions. So chain rule comes into place. Just dynamically looking at this thing, and then again here chain rule, because composition of two functions, and then we just use the chain rule again and again, how many ever times it was required. So here it was required 3 times, here it was required 2 times. So we just kept applying the chain rule, because beyond the chain rule we did not have any other complications in our expression. So, and finally we ended up with this, whatever our application of the properties led us to. So I would like to do one final example, which is again going to be the application of several rules. So we have y being equal to the square root of sine of x plus 1 divided by sine of x minus 1, and as I said, everything is going to be under root. So before differentiation, I would like you to recognize what rule we should apply first. So pause the video if you want and try to recognize what rule to first approach this problem with. So I'm assuming you figured that out. So let's differentiate with respect to x on both sides, because differentiation is an operation. So we have dy over dx being equal to the derivative of square root of sine of x plus 1 divided by the sine of x minus 1. Well, I'm sure you figured it out. So it's basically we have to use the chain rule. You know why? Because we have a square root first out front. There is no product, associate alongside the square root. We just have a square root, and we have the quotient of two functions inside the square root. So since we have a one function, here we have a ratio of two functions. Say we call that ratio to be one unit function. We have a function inside one function, so So chain rule naturally. So differentiating the external function, differentiating the square root will give us 1 divided by 2 times square root of the inside quantity. So sine of x plus 1 divided by sine of x minus 1. I'm applying the chain rule, guys. Times the derivative of the inside function. So the derivative of what was inside the square root function. It was sine of x plus 1 divided by the sine of x minus 1. Well, going further now, we don't look at what's outside the derivative, but what's inside the derivative, because that's what we're going to have trouble differentiating, right? So we have this weird quantity inside the derivative. So now why don't you tell me what rule do we use? Since it's the quotient of two functions, naturally we would apply the quotient rule here. So dy over dx is going to be, I can flip this up and write in the numerator. So square root of sine of x minus 1 divided by 2 times the square root of sine of x plus 1, and the derivative of this thing. So I said let's use the quotient rule, right? So differentiating the numerator first because it dominates while we make the denominator weight. So sine x minus 1 times the derivative of sine x plus 1 minus, now we make the numerator weight. So sine of x plus 1 is weighting while we differentiate sine of x minus 1, or the denominator. But don't forget the most important part, squaring the denominator. So we have sine x minus 1, the whole thing squared. Well, brilliant. We still have we have to still differentiate these two quantities, right? So we have 1 over 2 times the square root. I can take this under common root. Sine of x minus 1 divided by sine of x plus 1, and here we have sine of x minus 1 because we chose to ignore that first, times the derivative of sine of x plus 1. Well, look at this sum of two things, property number 3. So derivative of sine of x is cosine of x, and the derivative of 1 is 0. So plus 0, cosine of x plus 0 is just cosine of x, minus sine of x plus 1 because that's outside the derivative. And then again, as I said, property number 3. So derivative of sine is cosine, and derivative of minus derivative of 1 is 0. So cosine of x minus 0 is cosine of x divided by sine of x minus 1, the whole thing squared. So why don't we expand the bracket now? Just write everything as it is. Sine of x minus 1 divided by sine of x plus 1. We have a sine of x times the cosine of x minus the cosine of x, minus the sine of x times the cosine of x minus the cosine of x, but we still have to divide by sine of x minus 1, the whole thing squared. So well, these two terms are going to cancel out. So we'll have a negative 2 times the cosine of x. So that negative, so that 2 and this 2 will cancel off. So we'll have the square root of sine of x minus 1 divided by sine of x plus 1 times, you can put the negative up front, cosine of x divided by sine of x minus 1, the whole thing squared. So that's basically our dy over dx. So that's it for this video, guys. In the next video we'll be doing more examples of our derivatives, where stuff will be way more complicated. We'll be upgrading our level from this video, and by then I hope you practice the chain rule and the quotient rule, uh, especially, obviously all the other rules. But we'll be doing some smart ways of differentiation in my next video, where we'll have a square root of big multiplied quantities, and inverse trigonometric functions whose arguments are quadratic and like complicated and stuff like that. And there uh, I'll teach you guys how to differentiating in a clever way using substitution and stuff like that. So I hope to see you then. Meanwhile, please like, uh, subscribe, and share my channel with your friends, especially those who are starting calculus or who want to learn calculus on their own. Stay home, stay safe, have a great day. Peace out.